Hey everyone, and welcome back to my science studio. Before we jump into naming compounds, we first need to understand how to write the correct formula for ionic compounds and how to predict their oxidation numbers. You see, these two skills are the foundation of nomenclature. So let's take it step by step. So first, let's talk about how to predict the formula of a binary ionic compound, which is a compound made up of two different elements, a metal and a nonmetal, and they're held together by an ionic bond. And if you remember from the last lesson, ionic bond means there's a transferring of valence electrons. And metals tend to donate their valence electrons and form positive charges, also known as cations, while nonmetals tend to gain valence electrons and form negative charges, or anions. So to predict the formula for a binary ionic compound, we're going to need to do something called crossing the charge. And one thing I want you to remember is that the total positive charge must balance the total negative charge, and that the compound as a whole must have a net charge of 0. If the charge on the cation, the metal, does not match the charge on the anion, the nonmetal, we use subscripts to balance them. But please note that subscripts of 1 are never written. And a mistake that students often make is thinking they drop the plus or the minus sign, but we don't keep the signs at all. We only use the number part of the charge. So in this example, we have Na and Cl. Na is in group 1a of the periodic table and therefore has 1 valence electron. And because it's a metal and metals tend to donate, sodium will have a +1 charge. And chlorine is a nonmetal. It's in group 7a, which means it has 7 valence electrons. And it's more likely to accept 1 than to donate its 7 to fulfill the octet rule. Why? Because nonmetals tend to gain. When we cross these charges, so we cross the +1 from the sodium and the -1 from the chlorine, you'll see that we get a 1-to-1 ratio for the subscripts. Again, remember, we're not crossing the plus or the minus, we're just crossing the whole number. But because we don't write 1 as subscript, you're going to leave it as NaCl, or sodium chloride. And because the cation charge is +1 from the sodium, and the anion charge is -1 from chlorine, the net charge is 0. Why? Because a 1 minus a 1, you get 0. Which proves that the net charge for these binary ionic compounds should equal 0. Let's try the next one. Magnesium is in group 2a, so it has 2 valence electrons and will more likely form Mg2+. But bromine is in group 7a, so it has 7 valence electrons. And because it's a nonmetal, and all it needs is 1 valence electron to have a full valence shell of 8 electrons, it'll more likely form a -1 charge. So when we cross the charges, we'll get MgBr2. And what these subscripts tell us is that we have 1 magnesium for every 2 bromines. So when we draw the Lewis structure, we'll draw magnesium in the middle because it's the least electronegative element, and the bromines on either side of it. Now, each bromine has 7 valence electrons, and magnesium has 2. So how this ionic bond forms is because each of the valence electrons from the magnesium donates to their respective bromine, which each bromine can accept 1 to achieve a full octet. That's why here, the cation charge for the magnesium is +2, and the anion charge, bromine is -1, but we have 2 bromines present. So you have to do 2 times -1, which is -2. And when we take the net charge of this ionic compound, a +2 and a -2, you end up getting a net charge of 0. Now let's level up and talk about polyatomic ions. And the name says it all. Poly means many, atomic is atoms, and an ion is an atom with a charge. So essentially, polyatomic ions are groups of atoms that are bonded together that carry a charge, either plus or minus. And they behave as a single unit. I want you to think like wolves in a pack or gypsies traveling in a caravan. They always stay together. And some common polyatomic ions are NH4 plus, which is ammonium. OH negative is the hydroxide ion, and this is indicative of bases. So when you talk about acids and bases in your class, if you see a hydroxide in the back of a metal, that's usually going to be a base. But I digress. SO42 negative, that's sulfate. ClO3 negative, that's chlorate. And these last two that I mentioned, there's a whole separate lesson that I'm going to do on naming oxyanions, which is what these two polyatomic ions are. So stay tuned for that lesson. Now let's say you want to cross NH4 plus with OH negative. Well, similar to NaCl, you have a plus one and a minus one. So when you cross those charges, you end up getting a 1-to-1 ratio. So NH4OH, or ammonium hydroxide. The charges essentially cancel out because you have a plus one and a minus one. So that cancels out to 0. Now, what if a polyatomic ion needs a subscript greater than 1? Then you must use parentheses. Remember, like wolves in a pack, you have to keep the ion together. So for example, Ca2 plus and OH negative. When you cross the charges, you have to write Ca parentheses OH with a 2 on the outside. The 2 tells me that I have 2 hydroxide ions present. Remember, the OH stays together. It's a polyatomic. And this is super important because when students first learn this topic, they'll initially write the OH without the parentheses. And that's incorrect. It doesn't mean the same thing because subscripts actually serve a distributive property. So similar to math, the 2 distributes to the H and to the O. So we have 2 hydrogens and 2 oxygens present. And isn't that the same as saying we have 2 hydroxide ions total? It is. So for sure keep that in mind because if you do not write the parentheses, you'll incorrectly say that you only have 2 hydrogens and 1 oxygen present, when you should have 2 hydroxides present. Let's try this next one. When we cross these charges, we'll end up getting Al2 parentheses SO4 with a 3 on the outside of the parentheses. And again, this 3 tells us we have 3 sulfates present. And also remember that the 3 serves a distributive property. So if you want to find out how many oxygens are present, you distribute the 3 to the O. So 4 times 3 is 12. And you distribute the 3 to the sulfur as well. And because there's only 1, 3 times 1 is 3. So 3 sulfates is the same thing as saying we have 12 oxygens and 3 sulfurs. And I just want to make a quick note that the 4 that belongs to the oxygen in this polyatomic ion should not be touched. Meaning that when you cross over that 3 plus charge from the aluminum, you shouldn't be adding or multiplying or subtracting that 3 with the 4 at all. That's what the parentheses is for. You enclose the parentheses around the SO4, and then you have 3 written on the outside of the parentheses. And lastly, this next one, when you cross the charges, you'll notice that the subscripts, you get a 2-to-2 ratio. Okay? And again, you enclose the parentheses around the polyatomic ion as shown here. Just keep in mind that when you have something like this, you have to think, can I simplify the formula? Yes, I can. If I divide both of these subscripts by 2, I end up getting a 1-to-1 ratio. So the answer for this is MgSO4. And this makes sense because the 2 plus and the 2 minus charge, they cancel each other out. Now let's talk about how to predict oxidation numbers for atoms that don't have fixed charges. And on this chart, you'll notice that there are several elements that have fixed oxidation states, meaning their charge never changes. And we've already used a couple of these examples. So anything in group 1A will have a +1 charge. In group 2A, there will be a +2, group 7A, a -1, and so forth. Take your time and really read through this chart because there are certain exceptions. So, for example, hydrogen, it's usually a +1 when bonded to a nonmetal, but when it's bonded to a metal, it's actually a -1 charge. Also note that there are a few transition metals that are pretty predictable. For example, silver or Ag has a +1 charge, while zinc and cadmium have a +2. But really, most transition metals can vary, which is why we need to do a little bit of algebra for this section. You see, the sum of all oxidation numbers must equal the compound's total charge. And for neutral compounds, the sum must be 0. But for ions, the sum must be their charge. So I want you to think about solving for the unknown variable, solving for x. Let's take this example. You want to find the charge for chromium because you don't know what chromium is. It's a transition metal. It can be +1, +2. You don't know what it is. We know potassium is in this chart, and K will always be +1 because it's in group 1A. And it says here that oxygen will have a -2 charge. So we're going to set this up like an algebraic formula. We have 2 potassiums plus 2 chromiums plus 7 oxygens. And we're going to make that equal to 0 because the net charge is 0. Plug in the +1 charge for K, the -2 for oxygen, and we're going to set that equal to 0. All right, let's multiply. 2 times 1 is 2. 7 times -2 is -14. So now our equation reads 2 plus 2 chromiums minus 14 equals 0. Combine like terms, so 2 minus 14 is -12. So now we have 2x minus 12 equals 0. We want to isolate x, right? So we got to move the 12 to the other side. So add 12 to both sides to cancel out the 12 on the left. And we end up getting 2 chromiums equals 12. Multiply 2 by both sides, and we end up getting that chromium has an oxidation number of +6. Now the next one's a little different. Phosphate, or PO43 negative, now we're trying to find the charge of phosphorus. So let's do the same thing. We're going to do P plus 4 oxygens, because we have 4 O's, is equal to -3. Now we're not setting the equation equal to 0 because we have a charge. It's a polyatomic ion, so this should all equal -3. And we know that oxygen will always be -2, so we're going to plug in -2 for O. 4 times -2 is a -8. So now the formula reads P minus A equals -3. Add 8 to both sides to cancel out the 8 on the left, and we end up getting 8 minus 3, which is a +5. Phosphorus has a +5 charge. And one thing I like to point out in the rule is that phosphorus is in group 5A, and it's a nonmetal. And for the most part, it does like to gain 3, so become a -3 charge in order to achieve its full octet. But in this example, it actually likes to have a +5 charge. And the reason why is because if you look back at the table, those that have a -3 charge, such as in group 5A, those nonmetals have a -3 charge only if they are in a binary ionic compound. And oxygen is not a metal, so this is not forming a binary ionic compound, which is why phosphorus can have a different oxidation state, as you've seen in this example. Now that we've mastered all of these building blocks, we are finally ready to jump into naming compounds. Ionic, molecular, acids, bases, everything. And that's coming up in the next series of videos. So stay tuned for that. And if you found this video helpful, please don't hesitate to like, subscribe to my channel, drop a comment. Thank you guys so much for watching. I'll see you in the next episode. And until then, happy studying.